Imagine a dragonfly the size of a hawk, its four gauzy wings catching the late sun as it glides above a primeval wetland. Imagine a millipede longer than a man's arm sliding over a fallen horsetail trunk, its armored segments scraping ancient bark. Picture towering club mosses and tree-sized ferns rising like a green cathedral, while a luminous haze, thicker than modern air, hangs between the trunks. The world feels larger and stranger, and yet in its abundance there is a peculiar order. Giant insects were part of the architecture of life. This is the Carboniferous and the Permian, vast intervals of Earth history when atmospheric chemistry, climate, and ecosystems combined to allow life to experiment at unfamiliar scales. The fossil record preserves their traces, impressions of wings, flattened exoskeletons, and immense coal layers that mark ancient swamps, but those traces are fragments. They tell us who existed, but not always how or why the curtain falls. That gap is the heart of our story. So here is the question we will follow. How and why did these giants vanish? To answer it, we must become translators of deep time. Rocks are not random rubble. They are pages in a book that require many disciplines to read. Geochemists analyze tiny ratios of carbon and oxygen atoms locked in minerals to infer atmospheric conditions. Paleobotanists study fossilized leaves and spores to reconstruct the forests and climates they indicate. Experimental biologists model how insect respiratory systems perform under different gas mixes. Field paleontologists uncover the bones and plates that anchor these theories to real animals. Each method alone is partial. Together, they allow us to assemble a plausible narrative. Before we test mechanisms, it helps to appreciate why gigantism was possible at all. Two partners made it plausible: environment and anatomy. The late Paleozoic atmosphere appears to have contained substantially more oxygen than today, which would have made diffusion of oxygen through insects' tracheal tubes more efficient and may have supported larger bodies. Meanwhile, vast contiguous swamp forests provided expansive habitat and abundant plant matter for herbivores and detritivores. Warm, stable climates reduce the metabolic penalties of large size. When anatomy and environment align, evolution can push forms into strange and tremendous directions. That combination produced marvels: dragonflies with wingspans exceeding 2 feet, arthropods the length of dining tables, and predatory forms that patrol the dim understory. To imagine these animals is to imagine different ecological equations, one where physiology, atmosphere, and habitat all pushed size upward. Yet no environment is eternal. The same conditions that supported giants would later be altered by forces both gradual and catastrophic. The fossil record hints at those forces without handing us a single neat answer. In some deposits, fossils imply gradual ecological turnover. In others, abrupt shifts jump out. Ash layers, sudden changes in species composition, and signs of drought or flood. New vertebrate groups were spreading across landscapes and changing the dynamics of predation and competition. Continental drift and climate shifts reconfigured rainfall and drained swamps, fragmenting habitats. Each of these forces, alone or in combination, could nudge populations toward smaller, more adaptable forms. The challenge is to sort which factors were primary in which places and times. This film will trace those threads. We will begin by investigating the invisible variable that might be central, the composition of the air. We will examine how scientists measure ancient atmospheres, what the best evidence suggests about oxygen concentrations, and what those concentrations would have meant for breathing and flight. Next, we will bring the animals into focus, exploring their anatomy, life habits, and the physical limits that shape size. Then we will follow the slow unraveling of the ecosystems that sustain them, and we will weigh hypotheses about competition, predation, and climate change. At each step, we will test ideals against fossils, experiments, and modern analogs. Beneath those forests, clues wait in stone. Wing venation preserved like pencil tracings, armored plates imprinted in shale, coal seams that marked former swamps. These are the witnesses we consult. Scientists read them with modern tools, isotope chemistry that hints at ancient gas levels, microscopic plant anatomy that reveals humidity and seasonality, and experimental models that simulate insect respiration under different gas mixes. The evidence is imperfect and sometimes contradictory, but its totality forms a mosaic we can interpret. We will also meet the people who stitch this mosaic together: the paleontologist feverishly scraping shale in a field pit, the geochemist watching glowing mass spec readouts in a lab, the biologist setting up atmospheric chambers to test flight performance. Their work reminds us that paleontology is active science, an interplay of field discovery, lab tests, and careful inference. There is modern relevance to this inquiry. The same cycles of carbon storage, forest extent, and atmospheric composition that once favored giants are central to today's climate system. Wetlands sequester carbon, forests regulate local climates, and atmospheric chemistry influences which life forms thrive. Understanding how ecosystems reorganized in deep time when these systems shifted helps us see potential vulnerabilities and resilience in our own era. The vanishing of giants is not just a paleontological puzzle. It's a case study in how life responds when planetary parameters change. We will honor the sense of wonder these creatures inspire while remaining rigorous. Giant insects provoke curiosity because they force us to rethink possibility and contingency. They show us that life adapts to planetary parameters and that small changes, whether in gas composition or habitat extent, can produce outsized consequences. So we will proceed chapter by chapter, balancing narrative drama with careful analysis. Each segment will center on a specific line of evidence and end with a question that pulls us forward. Was oxygen the central lever? Did new predators tip the balance? Did climate and tectonics redraw the map of habitable swamp? We will test these ideas against fossils, experiments, and expert testimony. In concrete terms, expect case studies, reconstructions of iconic forms such as the giant dragonflies, the lumbering forest arthropods, and the coastal predators that hunted shallow seas. Expect field scenes in coal-bearing strata, lab footage of experiments recreating ancient air, and interviews that reveal how scientific consensus forms and shifts. Now step close. Touch the fossilized wing in your imagination. Listen for the imagined beat, and let the deep past begin to open its pages. Our first chapter will probe the air itself, how it was measured, why it matters, and the surprising implications for life on the wing. But what came next would change everything.